Thank you. Now, for something a little different, I guess. We're going from ultra-cold molecules to cold molecules again. Hi, my name is Nithesh Balasubramanian. I'm a part of the NLEEDM collaboration, where we try to use cold molecules to try and perform a measurement of the permanent electron-electric dipole moment in search of physics beyond the standard model. On the top right, you have our mascot for the experiment, which is barium fluoride, the current workhorse of the experiment. But of course, barium OH has 3 atoms, so I had to improvise, and so I added a little top hat to our little molecule there. So first, I want to step back a little and set some context for why we want to do this. An ideal EDM experiment will have, well, 3 major things. The first thing is that we know that for molecules, the best molecules are those that have a metal that's very heavy, and it is connected to a ligand that is extremely electronegative. So you have molecules like ytterbium fluoride, which you can see which kicked off this entire race, and barium fluoride, the molecule that we use. So barium is, of course, a very heavy metal. It is essentially a row above radium, where things get a little radioactive. So it's a nice place to be while still having good EDM sensitivity. So any molecule that is of the form barium X, where you have a heavy molecule that is also very polar, it should be very sensitive to an EDM, should we be able to measure it. We also have molecules like ytterbium fluoride and barium fluoride, which have a rather simple level structure, which means that it can be laser cooled, you can perform optical cycling on it. And this is very useful for statistics because you can increase the flux of your molecular beam. That is very beneficial for your EDM measurement. But of course, for those who are in the know, I can also see this in the bottom right part of the chart. We have molecules like thorium oxide and hafnium fluoride plus that have really established the new limits of the EDM values. And those cannot be laser cooled. They have a very complicated internal structure, and that is used to their advantage because these have internal co-magnetometer states. And these are states that are of opposite parity, that are closely spaced, and this allows you to come up with very interesting mechanisms through which you can perform a lot of robust systematic error rejection. So like I said, an ideal EDM measurement would use a molecule that has all 3 of these properties. And this is where I propose barium OH in some sense, where it is a heavy molecule, it is a polar molecule. The electronic structure is very similar to barium fluoride, its cousin, so it can be potentially laser cooled, and also it has an internal co-magnetometer state. And this is really the reason why we recently published a paper on PRA. If you're curious, you can scan the QR code, where we envision an experiment where we start with a cold source of barium OH molecules that we later focus with a hexapole, decelerate with a traveling wave decelerator, trap it, and in an optical lattice, and perform an EDM measurement on it. This is very exciting. I'm very excited about this stage of our collaboration. But of course, to perform an EDM measurement on barium OH, you first need some barium OH. So that's what I would like to talk to you all about today. This is our pride and joy, the cryogenic buffer gas source. At its heart is a copper cell that is kept at 20 Kelvin. And inside, we have a rotating barium metal rod from which we ablate barium atoms using a pulsed nanosecond laser. This happens in the presence of cold neon, usually also around 20 Kelvin. And we also send in a reactant gas mixture. And this is a mixture of neon and water. And we do this so that we can precisely control how much water we send into our setup. Now, the chemical reaction, barium plus water, gives you 2 reaction products. One is barium oxide, and the other one is barium OH. Barium really likes becoming an oxide, so we have to convince the barium a little, and that's what the enhancement laser is about. We send it right into the cell, where we excite the barium atoms so that it preferentially forms more barium OH than barium oxide, which I'll discuss about in a bit. This forms a beam once it exits the cell. We have 2 detection points where we have a laser from a titanium sapphire laser. One is absorption, that's about 10 millimeters away from the source, where the molecular densities are high, but we also have, due to the diverging nature of the beam, we also have a lot of Doppler broadening. So it's good to characterize a lot of things, good to find spectroscopic lines when you don't really know what you're looking for, but that's also why significantly further down the experiment, 770 millimeters down, we perform fluorescence, where our Doppler broadening is significantly less impactful. So this is our entire experiment. or the experimental setup, and I'm happy to say we managed to make a lot of barium OH. And really, the biggest new interesting thing, and maybe not a new interesting thing, is that we actually managed to get a significant enhancement in the amount of barium OH that you can produce. So the black line that you see over there is when we tried to make barium OH when we did not have access to this barium excitation light. So this is the transition from the singlet S down ground state to the triplet P excited state. This is the 791 transition in barium. And the moment we sent in the barium excitation light, our signal basically increased by a factor of 11, which of course made performing measurements much easier. We had to check that indeed this was because of atomic excitation. So we kept track of how much barium OH we were making by keeping a laser locked on one specific barium OH transition. And then we tried sweeping the barium laser across the 791 transition. And in doing that, we do see a very clear resonance profile right across the specific transition. So we're glad to know that we're not just heating the cell up or something to try and increase our molecules. This is a bona fide atomic resonance. There is a lot of broadening that we see here, and we mostly attribute this to the in-cell temperatures, because of course when have an ablation inside, even if it's a pretty cold cell, the ablated products are extremely hot. So that's where we mostly attribute this down to, but we also send in a lot of laser power in order to saturate this barium transition. So this is also potentially a lot of power broadening involved here. Just saying 11x enhancement felt a little bland. So what we did was we have a number of knobs to control our source parameters. This is usually how much neon do we send in and how much water do we send in, and also how much power do we use to ablate our barium rod. And essentially we see that of course, the amount of the molecules you make changes depending on which knobs you change, but the trend, the improvement in signal is more or less constant across all of these parameters. The only place where we don't really see this trend is in the top right, when we try changing the amount of ablation energy that we put into the barium metal per shot, where unenhanced, we see that at higher ablation powers, we see less barium OH, but when we do enhance, when we do send in this atomic excitation, then we do see more power, more molecules with more ablation. And I think this just goes to show that the environment inside the buffer gas cell is extremely complicated, and the chemistry that is involved in there is pretty non-trivial. There's one more thing we wanted to check, which is what is the best way of actually sending in this barium excitation light. And we have two different configurations over here. The first one, which is labeled in cell, is when we are orthogonally sending in the barium excitation light that happens inside the cell entirely. And the other one is the so-called counterpropagating setup, where thankfully, because of the way that experiment was set up, we have an optical access window all the way on the other end of the experiment, which means we could send in the laser light all the way from the end. And what we see is that if we scan the power of our enhancement laser, we actually see that the yield of barium OH saturates way earlier in this entire sweep. Whereas if you try to send it through a counterpropagating configuration, it takes quite a lot of power before we start seeing the same number of molecules as we would in the in-cell configuration. The counterpropagating setup also has a number of disadvantages. Of course, if we are sending in 60 milliwatts of laser light into a 20 Kelvin copper block, it's bound to get a little warm in there. But also because there was a PMT tube in the way, we got a lot of background from just sending in this enhancement light. So we figured that, well, this in-cell barium excitation is actually the best way to go, because we also perhaps would not want to spend so much power on just this one specific transition. Now, as for why, perhaps I'm not sure how many of you are familiar with the world of spectroscopy per se, but barium OH is a molecule that has been studied for a very, very long period of time, like since the 80s, ever since we had access to broiler ovens and other warm sources. And it has always been a rough rule of thumb that if you wanted to make a group 2 monohydroxide, you just try to excite the atoms inside also. It doesn't matter which group 2 metal it is, it just works. And it took till 1993 when Davis et al. tried to come up with an experiment to try and figure out exactly why it is that it works. Now, in his experiment, they excited from the singlet S state to the singlet P state, but the goal ultimately is that the barium eventually decays to a metastable D state. And in the right, you can see that really what happens here is that once you have this barium in the D state, somehow the intermediate complexes that get formed when you are trying to make your barium OH is a lot more energetically beneficial if you do it from the D state rather from the S state, where it is more beneficial for it to primarily form barium oxide. This is surprisingly a reaction pathway that you only see with water and not many other reactants. And so an interesting thing for us to personally check was to see, well, can we do it from the 3p state? Because that state is much longer long-lived because it's a singlet to triplet transition, and that decays to a triplet D state, so it's potentially going to be even longer lived. So hopefully we'd have the barium atoms will have a better chance of reacting with as many molecules as possible. And in the end we have, although we don't have a very nice diagram like that to the right. So if there are anybody here who would like to help us make a very similar chart, I'd be very happy to talk to you. So now that we can make a lot of barium OH, we can finally get to the fun stuff. We can start performing some precision spectroscopy to try and understand its internal structure. Our group has primarily worked with diatomic molecules, so triatomic molecules is a little bit of a culture shock. Once we have mapped out all of these structures, hopefully we can identify some protocols for laser cooling, optical cycling, and more interesting things. And finally, as a way of the proposal that I had just shown you, I would like to also see how we can manipulate this molecular beam with a hexapole and decelerator. But also a lot of these things have been put on hold a little because we have moved this experiment from the Free University in Amsterdam all the way to the University of Groningen, which is where I'm from. And I'm very happy to announce that literally this Friday, we have seen barium OH in our brand new cryogenic source. So I think I would like to end my talk there. Thank you all so much.
Thank you very much. Questions? In the very back up there.
Okay, I'm not sure if this works. Do you also see the same enhancement for barium fluoride, this optical enhancement?
We in the very same setup so the setup that we perform these measurements in was originally built to produce barium fluoride and to understand its understand how the molecular beam behaves. And the day we tried measuring this and we saw this enhancement, we immediately tried it for barium fluoride, and sadly we did not see anything. And I have a feeling that the reason why is because the way we make barium fluoride, you use sulfur hexafluoride, SF6, and I have a feeling that barium fluoride is already the most optimal reactant product. Whereas in the case of barium OH, the issue is that we have this competing reactant product, which is barium oxide, that we want to kind of steal the attention from. And I believe that there have been some other works that have been done where the similar kind of experiment has been tried to see if there was more enhancement, and it just has not worked. Barium OH seems to be a bit magical in that sense.
Okay, I see. And your sign state is the n equal to 0 state, right?
Our sign state for, let me see if I have a, it is the n equals 1 state in the bending mode of barium OH.
Right. But then the point is, like, then why use a 20 Kelvin neon gas? Why not a helium buffer gas source?
That is an excellent question. I think the simple answer is that we don't have a cryostat that gets that cold. Eventually, that's an upgrade that's down the line. But right now, in principle, this gets us a good enough rotational temperature that we can work with this. Like we have, especially because of this enhancement, although we haven't quite measured this properly yet, we know that this enhancement with the barium atom also increases the population in the bending mode by quite a bit. So the vibrational temperature is actually a lot warmer than you would normally expect.
Also, I'm sorry to steal your time, but like last comment about in your longitudinal beam, I think the reason you need so much power is because of Doppler shifts. If you just broaden your beam in the counter-propagating direction, and then it will compensate, like it will address all of these various velocities that you have going forward in your buffer gas cell still. And then you should be able to sort of get a quick saturation at lower powers. I've tried
When
the
you
same
say
thing.
Doppler shift, do you mean because of the fact that it's going?
Yeah, because the molecules are still traveling with your buffer gas.
Yeah, yeah,
In the,
but so the signal that I'm showing here is from a fully optimized signal. So we perform a sweep, we pick the highest signal that we can find, and we try to plot it from there. Or am I not understanding your comment
we
correctly?
can discuss this later
Okay,
on.
yeah.
Okay. Up front here was the next question. Oh, we can do it with, there's another one up there.
So what happens if you use methanol instead of water? Is there also an enhancement?
So thanks for your question. The reaction with methanol was actually investigated in this specific paper. So, I get to use this janky thing now. So we have water. So water methanol was tested for both things. I think when we started out, we wanted to try methanol as well because methanol has a lower vapor pressure, which is nice for our systems. But we found no barium OH coming out of this, and this is something that their paper also shows. That the primary product again is barium oxide and barium OCH3, not a lot of barium OH. And I don't quite remember off the top of my head, but I don't think the enhancement works there at all. Like they don't see an increased amount of barium OCH3 with this particular setup. But yeah, I think maybe what might help is hydrogen peroxide if we want to try and make more OH, but we're a bit worried about what that does to our cell.
Okay, there is a question back there. Where's the cube? Ah, it's already.
Hi, forgive me if you said it and I just missed it, but for barium OH, for the EDM measurement, is the effective electric field known?
As in the when it's fully polarized, I'm assuming. So the sensitive.
The thing you multiply the EDM by to.
Yeah, so there have been theoretical calculations for that from our own group members, some of whom are here in the audience today. So that is known. Yeah.
Would you care to say how much it is?
I do not remember that off the top of my head. Sorry. It is comparable to, if not a bit better than barium fluoride. It is a bit worse compared to barium CH3. But again, I do not have the numbers off the top of my head.
Okay. I think there are no further urgent questions. So we first thank the speakers and all the speakers of the session.